Hello and a very warm welcome to everyone who's joining us for today's webinar. I'm super excited because today we will be introducing our very first in-house robotic manipulator designed specifically for teaching and research. My name is Armin, and together with my colleagues Peter, who is a senior research and development manager at Quanser, and Pasha, our regional manager for the Americas, we will be your hosts and webinar moderators for today. And with that, let me pass the microphone to Pasha to do further introductions.
Thank you, Arman, and hello, everyone. Welcome from wherever in the world that you're joining us. Thank you so much for being here. We are super excited, as Arman said. We've been anxiously anticipating this day as it is a big day for us. It's a launch day for us, and we are launching our very own robotic arm, as Arman said. Not only we are launching today a robotic arm, a brand new arm, but we're also launching a platform that enables you to take a modern approach towards teaching and research in robotics. And we'll be talking a lot about that in a couple of minutes. But just to tell you where we've come from, I myself, when I joined Quanser more than 10 years ago now, during my first week, the first project that I had to work on was documenting this platform that at the time was a platform to interface to this robotic 6 degrees of freedom Mitsubishi industrial grade heavy duty robotic arm. And at the time, this was a pretty big research undertaking by Quanser. You know, a few Quanser engineers were involved in this. A few months of work had gone into this by the time I started, and it was a big deal. It was a big research project, and over the years, that became more and more routine, and that became a thing in Quanser that we would interface and bring an open architecture platform for research to any type of third-party robotic arm, industrial robotic arm, heavy-duty robotic arm. And this went on and on. But one thing that was also happening in parallel to this was the rise of robotics in education, and the trend, it becoming a trend and a more and more routine thing to see courses in undergraduate levels across mechanical and electrical departments to teach robotics. You would also start to see expectations rising from the departments and institutions to have minor or major programs in robotics, and that's what made us think about this seriously. You know, the arms, the research, the research applications of those heavy-duty arms was successful, but to bring it into education and to kind of commoditize it, that's what made people like my colleague Pete think seriously about, for the first time, designing and manufacturing our own education and research-friendly robotic arm, and as I said, platform to enable everybody, institutions with existing and new courses and programs around robotics, to take a modern approach towards robotics. And with that, I'll pass it on to the person who is the mastermind, and as I've started to referring to him, the father of the QArm, the architect of the QArm, my good colleague Peter Martin, who will take us through this new platform, and at the end we'll be happy to take questions as they come. Thank you so much, and over to you, Peter.
Thanks, Pasha. Thanks everyone for coming. I'm also very excited to finally be able to share this with you. Just to give a little bit of another history and a little bit of a flavor as well, in terms of starting our in-house development of our own manipulator. That's also been quite a long road. When I was a youngin at Quanser as well, one of my colleagues who shared the sort of the space where I work was asked to start looking into developing our own in-house developed manipulator system about 9 years ago. And at that point, it just wasn't going to be feasible for us. The components weren't there. The price point for being able to develop something to the level that we wanted it to be for what we look for in a product just wasn't there, and it wasn't going to be feasible. And so we abandoned it. But then about 3 years ago, one of our former colleagues started looking into whether or not technology had progressed to the point where we could offer something that would be both cost affordable and also performant enough to be able to meet the needs of our customers. And it looked at that point like we might be able to do something. So we kicked off a project, and despite all the delays, all of the COVID related complications and this and that, we are finally able to now share with you publicly what we've developed and what we really think is going to be a fantastic platform moving forward for the next few years, to be able to offer, like Pasha said, really modern and engaging experiences for students, both in teaching and in research, based around robotic manipulator systems. And so I'll start there with the title. It's designed for modern engineering education and research. And that's really where we started when we started developing this product. Was we wanted to make something that was designed from the ground up to be a modern approach to being able to give education experiences to students and to give research opportunities to graduate students in the field of robotic manipulators. And from the ground up, that was our goal. That was our purpose behind creating this system. Adaptability, robustness, support, all of the really elemental things that have made us a leader in academic equipment for over 30 years. That's kind of part of the DNA of the system. That's part of what makes up all of our systems. Our method for how we create these things always includes those elements. But for this, we wanted to really make sure that when we created this system, it would be ready not just for modern courses, things like AI and machine learning, IoT, Industry 4.0. We're all aware of all of these exciting emerging courses that the students are really interested in learning about, and also that have a high demand once they graduate for people who have specific skills and experiences to be able to really excel and succeed in whatever path they choose post education. But then also being able to do teaching project-based experiences for students, capstones, studio classrooms, these really modern teaching approaches that give students those hands-on skills in a new and different way to make sure that they actually have those skills. They really understand how these systems work, and they haven't just sort of seen or peripherally had these experiences. And finally, giving modern delivery, whether it be at distance or hybrid learning. That's a huge, huge barrier to a lot of institutions nowadays, being able to offer hands-on manipulator experiences, which are inherently something that's based around a hardware experience at a distance or through hybrid experiences. And the work that we've done this year has really brought us to be able to offer that as part of this system. And then finally, obviously, research in controls, robotics, cyber physical systems, all of the classic and emergent research topics, all of those things. It was a tall order, but all of those things were what we wanted to really encompass when we built out this system as a general system, as a general all-purpose manipulator, but also one that was, again, focused specifically on academic need. And so in order to do that, we really started by focusing on some of the key features we would need for that kind of system. What are some of the things that would give us that ability to address those modern approaches to teaching and research? One of the things we really wanted was a high quality RGBD camera, something that would allow not just the classic pick and place or movement based, kinematic based manipulator activities, one that would also open up the possibility of being able to do things like machine learning or IoT, or being able to do even classic topics like visual servoing. That was one of the main things we really wanted to have on the ARM to make it versatile. Obviously, it needed to be robust. We have a lot of experience, obviously, over the last few decades in building systems for undergraduate education, and they can't be lightweight. They need to be something that's robust, that's going to stand the test of time and the test of year after year working with undergraduate students who are a little bit aggressive sometimes with how they treat equipment. So we wanted to make sure it would last and it'd be durable. And we wanted to make sure that, again, not just the software, and I'll get to that in a minute, our software has always been very flexible and expandable, but also the hardware was expandable and flexible. So you can see here, we've outfitted it with an IO board, an interfacing board at the end effector that allows very easy additional sensing, additional actuation, customization of how it interfaces with the world at the end effector through an intuitive breakout or interfacing board, much like a traditional microcontroller, but one that's completely designed in-house to be able to offer exactly the experience we wanted it to have. And then finally, our two-stage tendon-based gripper to really be able to manipulate a wide variety of objects, so that it's not just basically being able to pinch or being able to lift something that's a particular size or configuration. This versatile gripper really allows you to pick and manipulate a wide variety of things and pinch, grasp, grip, all sorts of different ways of working with the world. And then on top of that, obviously, our curriculum, we're known for providing cutting edge and groundbreaking curriculum. All of our products have always come with a rich variety of resources to be able to make it as easy as possible to adapt our systems to a traditional course structure. And so with this, again, we've pushed the boundaries a little bit in terms of the topics and the approaches that we want to provide in terms of our material to be able to address not just your traditional manipulators course, though we do that very well, but also expand out into different types of courses. So this is a little bit of a nuanced diagram, and I'll get into the curriculum more as I move through the slides. But in this case, I wanted to just illustrate that at the outer level, we are basically going to be addressing all the traditional topics that are covered in most manipulator courses based around your Spong or Craig style resources that cover things like kinematics and trajectory generation, low level control, things like that. But then moving in from there, we want to get into some more complex topics like tool manipulation, singularity avoidance, things like that. And getting even deeper, we get into some of the more dynamics-based or visual-based elements like visual servoing, load balancing, and then finally getting into the rich heart of modern engineering and modern manipulator systems, things like adaptive control and machine learning and stuff like that. So as we get into the center, the depth of the content may start to change, because obviously for things like digital twinning or adaptive control, it's not typically something covered by an undergraduate course. And so we don't necessarily need to provide the rich curriculum that we would typically, but having nice examples that are well documented, well structured, that have experiential questions and things like that to make sure that students understand the concepts, that's more what we're going to be aiming for, to really be able to give students at different levels and different scaffolded levels of their progression through undergraduate and graduate work, the tools they need and the experiences they need to be able to succeed at that level. We've also even expanded this out since we created this diagram to provide even some more basic operational experiences too, things that you might typically cover in a technical school or what we call here a college or a community college. So we're really expanding the breadth of the material that we want to create to really be able to offer a lot of resources that can complement this hardware experience. But it doesn't just end there, because as I said, we're also building out a rich hybrid experience where if students aren't able to be on campus, whether it's because of COVID or because maybe in the future they're at a distance, whether they're geographically distant from the school or it's an impediment to be having to commute long distances or things like that, or even large class sizes. With our QLabs platform that we developed this year, we finally have the ability to give every student their own virtual manipulator that behaves almost exactly the same way as the physical manipulator system. And that really opens up a lot of opportunities to be able to give more diverse experiences to students without having to necessarily worry about the traditional safety concerns. Obviously, our manipulator is designed for an academic environment, so we've made it as safe as possible, but some of the operations you might want to do with a manipulator, whether they're very high speed or they come very close contact with the environment, we may or may not want students to develop algorithms to do those things, because you never know what's going to happen when students get deep into the inner workings of a system like this. But being able to do it virtually can give them that confidence that what they've developed will work and it will work well before they implement it on hardware. But then also being able to give a system to every student, they have the world at their fingertips to be able to spend hours, if they like, playing with the system, really experiencing what it does and building their own software, their own approaches to how they want to do things. When you have a robotic manipulator like this, basically at every student's desk at home, there's a whole lot of things that can come out of that in terms of opportunities to really explore and understand how the system works. And then finally, as I said, for telecommuting, being able to offer students the ability to do their activities at home or at a distance and then come into campus, whether through remote access or physical access, to be able to validate their systems and hardware. That's always going to be part of this experience. We're a hardware company at our heart. And so we really believe that the hardware experience is essential to being able to understand these systems, but you can get a lot of that understanding virtually before you go on campus and really work with the physical systems. So this is something we're very excited about. This is the first system we've ever developed where it was actually released virtually first. This is the physical unveiling today, but the virtual system, the virtual QArm, has been available for 2 or 3 months now. And that's also a strange experience for us. It hasn't been something that we've done before, but obviously this year provided both the means and the need to be able to really offer something like that. And so we're very excited about what that means for being able to move in exciting different directions. And so just to summarize this first overview of the system before I get into the real nitty gritty of the ARM and also our resources that we offer, basically what we'd like to provide here is what we see as being the easiest way to introduce modern hardware into an undergraduate robotics and graduate research course. I came up in robotics and took many robotics courses at different universities. And I know this isn't always the experience, but when I was in school, the manipulators that we used were always out of date. They were always the older models, the ones that have been around since the 80s or the 70s even, that they got the job done. You understood how kinematics worked and how being able to do trajectory generation and pick and place tasks and things like that. You understood the concepts, but it wasn't really exciting to see something that was kind of rickety, a little bit weird looking, going through these operations. Whereas being able to offer something like this system that not only behaves in a very reliable and repeatable and robust way, that has these features we're really excited to offer, like the camera systems, the interfacing board, but even looks modern. It looks exciting. It really gives students that motivation, which is key to any of their activities. It has, obviously, like I said, a rich variety of course resources. I'll talk about those in just one second. And then a lot of, obviously, abilities to offer not just those teaching resources, but also software examples to save time on research activities. And then finally, it's cost effective. So we've really, I believe, delivered on all of those goals I talked about initially. Getting into those academic resources, really the cornerstone of how we've designed this academic platform. As I said, the first thing that I want to talk about is our philosophy. Basically, what we decided to do with the curriculum and with the material we developed was to go from an application context. So really not just talk about something like kinematics or something like trajectory generation, but start with the activity, the application of those skills, the motivation behind why you would want to learn about these topics, and then move from there into the theory and then into the application of those topics. So for something like this traditional diagram that shows how a manipulator system works in terms of path batting using inverse kinematics to command joint controllers, getting into some of the elements of the actual physical system itself in terms of the dynamics of the system, and then back through forward kinematics to the path planning systems as well as imaging. This is your traditional control loop or feedback loop that you would see in a manipulator, but these aren't the topics we're teaching. They are under the hood in the background. These are what we're teaching, but what we're really teaching are things like these types of topics: teach pendant, trajectory generation, workspace identification, being able to give students, again, immediately the application for the skills, the motivation for why these are important and why learning about these is going to offer them opportunities in the future. So with this first set of material, that offers about around 15 lab hours. This is the first complement of material that's, some of it's introductory, some of it's a little bit more basic, but at the same time, they're offering that foundation of skills of how this kind of manipulator feedback system works. And then we layer on top of that in a scaffolded way additional activities, things like tool manipulation, singularity avoidance, getting them into not just generating paths for the manipulator, but being able to modify those paths and adjust them and identify places where they break apart, and ways that you can use the tools to be able to position things in very specific ways. So really progressing from there into actually using a manipulator effectively. And then finally, as I said, we want to layer on top of that another complement of activities that highlights some of the more advanced topics, like being able to compensate for dynamics or loading on the system, and then finally visual servoing. So really giving a full complement of material that starts at the very introductory labs, things like I said, teach pendant, lead through, stuff like that, but then build up from there through our second and third releases of more rich content, and then finally our research examples we're hoping to provide later on in the year based around, as I mentioned in a minute, not just our traditional MATLAB Simulink material, but more additional topics as well to really bring it into the modern era. In terms of specifications, delivering on those research topics, there are a variety of specifications we needed to be able to do those activities. This is an overview of some of the core specifications we have here. You can see that it is a 4DOF serial manipulator. It has a very versatile reach, 750 millimeters. That should be more than enough to be able to accomplish most tasks that you would have on a lab bench style activity. It has a pretty reasonable payload for those types of activities, between 350 and 750 grams. That range depends on the amount of time that you're going to be operating the system continuously. So at 350 grams, you can pick up a payload and move that payload around and do operations with that payload continuously, indefinitely, all day long, 5 days a week. 350 grams is no problem. Beyond that, we start to run into thermal issues. And so basically, it can lift and manipulate up to 750 grams, but the time with which you can do those manipulation tasks continuously without stopping starts to drop down to, I think at 750 grams, it's around 20 minutes of continuous nonstop operation before we start to get close to some of the thermal limits of the actuation system. So it's still very doable, and 20 minutes is still a reasonable amount of time to be able to do continuous nonstop operation. But obviously we wanted to offer a wide variety of payloads, but at the same time fit within our constraints in terms of safety and things like that. 90 degrees per second as well is our nominal operating velocity for the different joints. Again, that is safety limited, not just in terms of the safety of the manipulator system and the safety of students, but also things like regulatory requirements come into play there, where theoretically the system could move more quickly, but we're because of certification issues and things like that, we have capped it at 90 degrees per second. But we do offer, that being said, both joint-based internal control. So all of our smart servos have the ability to do their own internal closed loop control, but also external control in real time through our QFlex and MATLAB Simulink interfacing we've traditionally done with Quark. So you can not only use the internal control loops that have feed-forward PID-based control, but also externally you can command the system using just a straight PWM command to the different joints. So you have the option there of building your own custom control algorithms and things like that in MATLAB Simulink, and relying on Quark to be able to provide that real-time interfacing. The extensive features that we have ensure safety of the arm and the user. Again, because it's a completely open manipulator where you can customize all the different levels of the system, from the very high level operation all the way down to the joint level control gains, the joint level commands. Safety is a little bit flexible. We're trying to make it as safe as possible in our examples and in our material, obviously. But because it's completely open and customizable, obviously you can bypass those if you see fit, but we would recommend trying to keep in place as many of those safety measures as you can. Some of them we will actually have in the actual manipulator firmware itself. So there are some elements like joint limits where they can't be bypassed. They're always internal to the system, and they're going to remain there so that we don't actually damage the system by running against hard stops or things like that. But there is some flexibility there as well. And finally, as I talked about, the Intel RealSense D415 camera, that it provides a wide variety of applications, from depth to high quality RGB vision and things like that. And then finally, also, as I said, the custom interfacing board that I alluded to, that gives you the ability to have a lot of flexible interfacing options, from analog to encoders, I2C, SPI, UART, PWM out, regulated power at 12 volts, 5 volts, 3.3 volts. So it's basically a full microcontroller system without being able to necessarily create the onboard embedded software to run it, but basically with all the interfacing opportunities that you would have. And then you would create the logic for that basically off device, as you would any of the other logic from operating the manipulator, either in MATLAB Simulink or the other variety of software applications that we have to offer. And then finally, as I've been talking, you've seen the gripper in action, being able to do different types of manipulation tasks, being able to both pinch and grasp and work with a wide variety of different shaped objects and things like that. And that gripper system also has current sense. So in this case, we're doing different grip strength demonstrations, not just going to a particular closed position, but also being able to articulate and regulate the strength of the gripper using a feedback current control system, so that there's also some customization there you can do if you have different types of gripping applications you want to experiment with. And in terms of that software compatibility that I was mentioning, obviously our bread and butter is MATLAB Simulink. Our legacy, both in terms of our Quark platform and also the way that we interface through systems like QFlex, which is our USB or embedded interfacing platform. MATLAB Simulink has always been our first and foremost target. So you can see, obviously at launch, we have full support in MATLAB Simulink in real time using Quark. That's through our USB interface for the QFlex panel to offer real-time external command and control. So everything you do can be done completely open and customizably in MATLAB Simulink using Quark and through QFlex for the USB interface. That lets you easily deploy from hardware to our virtual environment and back again. I'll show a couple of examples of that, but basically with just changing a couple of very small parameters, you can take your hardware examples and move them to the digital twin in our virtual environment and then back again. And obviously, it also opens up support for MATLAB robotics toolkits and the other toolkits that are built into the platform. We'll actually have the 3D models and dynamics of the arm in MATLAB 2020B. So if you happen to have the MATLAB robotics toolkit for MATLAB, you already have virtual representations of the QArm with full kinematic and dynamic representations in that toolbox ready to go. But then also, since we started 30 years ago, the world has changed in terms of the variety of platforms that we need to complement, especially in robotics. And so throughout the rest of this year and early into next year, we're going to be releasing a variety of examples and documented exercises for students in Python, and also getting into ROS with Gazebo and Arviz to be able to show all the different ways to interface the system. So if you want that real-time turnkey plug-and-play experience, MATLAB Simulink with Quark is the way to go, just like all of our systems have always offered. But obviously, if you're more comfortable with an API and being able to create software in Python or .NET or C++, then we'll be providing examples to show you how to do that and how to interface the system that way. The experience should be more or less the same in terms of the operation of the arm, but the flexibility may be a little bit different in terms of because of our real-time performance and guarantees we offer in Quark, we may or may not be comfortable offering some of the same openness and external control that we have in Python because of safety and things like that. But we'll work towards there and see what we can offer once we have those examples pulled together. So expect those in the coming few months. And with that, what I'd like to talk about next is some of these scenarios that you might be able to see both in conventional and hybrid teaching, so for how you can use this particular platform for different types of activities. So the first one I'll show is kind of a more traditional activity, but you can see here our lead academic developer for this platform is doing this activity both on the virtual QArm and also on the physical QArm. So in this case, he's doing a singularity experiment where he's showing how the velocities and how the different elements of your singularity identification algorithms react to moving through singular points. And so he's just moving the arms a variety of ways to show what happens when you approach a singular configuration. But as you can see, the behavior is very similar from the virtual QArm to the physical QArm. And so students can basically do this activity in particular on either. It doesn't really have a huge significance whether or not they have this activity on the physical system or the virtual system. The observations they'll make and their level of understanding of what singularity means to a manipulator is unchanged. And so that's a nice little demonstration of how you could do this type of activity. The other thing that's interesting to note here actually is that, as you can see here, he has it on camera. He's demonstrating it in MATLAB Simulink through just a work demonstration on his desktop. So this could also be done in a lecture as a demonstration very easily. My colleague Murtaza, who's shown here, doing this experiment, he's actually lecturing currently at the University of Toronto using the QArm for their fourth-year robotics course, and has been doing these types of demonstrations all throughout his course, both in lecture, in lab hours, and also for the students to be able to emulate using both the virtual system and the physical system. So it's a very good example of how you can bring the flavor of hardware into your lectures as well as the labs and tutorials and things like that. Moving on from there, I'll show a different example. In this case, it's kind of the same style of approach in terms of how we're showing the manipulator operating, but in this case, the scenario could be something along the lines of creating your algorithm virtually and then implementing it in the physical system on campus to be able to validate your algorithm. So you can see on the top right, he's created a very simple pick and place algorithm. And what he's actually implemented in the real world on the bottom, it isn't exactly the same. It's not picking up exactly the same object and putting it down in exactly the same way. But being able to have, as I said, that confidence that what you've created is going to give you the type of behavior that you're looking for. And then once you're on campus or using the physical system through remote access, being able to customize it and fine tune it to do exactly the operation that you're looking for. That's really useful and really, really exciting for students to be able to have that confidence and not have to worry about getting to campus and not having it work and not understanding why and going down a rabbit hole of trying to fix the system. And then on top of that, typically your simulation systems and your hardware systems are very detached. You'd have to implement them in very different ways, which could cause complications when you get there. In this case, he's running exactly the same code on both, exactly the same Simulink diagrams. All he's done is just add a configuration parameter to be able to say, use the virtual system as opposed to the physical system. So there's a lot of confidence there as well that the actual behavior is the same because the software is the same. And then finally, I'll just take a little bit of a brief step aside from the QArm to talk quickly about our QLabs environment, which, as I said, does feature the virtual QArm, but also has some exclusive activities that really complement the physical activities that are available through the virtual QArm. In this case, as you can see, we have obviously the traditional workspace where you can do exactly the same activities you would on the physical system. So here there's that parallel of being able to do the digital twin parallel activity, things like workspace identification, pick and place, trajectory generation, that sort of thing, where you don't really need a custom environment. But if you do invest in something like the virtual arm, there is the opportunity to do something really exciting like this, where we have a conveyor belt, we have different shaped and colored objects. You're doing pick and place tasks to put them into different types of receptacles. You can do things like tracking, servoing, identification, all that kind of thing. So what does that look like? You can see here a newer version of that environment that I just showed you. This is one we've been developing for the last few days. So this is very new and very fresh, but as you can see here, we're customizing the configuration of the conveyor belt, the configuration of the objects, how quickly they're moving. On the bottom left, you can see a live stream from the virtual camera. The camera is configured exactly the same way as the real camera is, so you don't have to worry about your image processing failing. It has exactly the same view angles and depth measurements and things like that. And in this case, what we're doing is identifying the red blocks and then building up the ability to follow those red blocks in real time and track them. I apologize, my video is not following perfectly. I think it's a lot of things going on all at the same time, but it gives you a flavor of the types of activities that you can do with this sort of system.
Okay, thank you, Pete. That was a great presentation. I do have a number of questions that have come in, and we could go through those. There's a couple of questions regarding pricing, and Pasha, this question's probably for you. Could you please comment on the pricing for the ARM?
Absolutely. Thank you, Pete, and thanks for the question. Regarding the pricing, we'd be happy, depending on your region, to provide you with the pricing through ourselves or our local distributors. depends on which region you come from, that would be your point of contact. But to answer your question about the pricing, as Pete was saying, we were aiming to make sure that this ends up being less than 20,000 per workstation, including the curriculum, the ARM, the software, and the content that Pete was showing. But again, if you would like to talk about more details about the breakdown of this with your local representative or your Quanser channel manager, feel free to contact us.
Okay, Pete, I have a question for you. Could you comment further on the safety aspect of the ARM? Is it something that students can use on their own without any supervision?
Yeah, so because of the context, obviously, in an academic setting, our goal was to develop an ARM that students could use without an enclosure, without your traditional gated operating environment like you would need to have for an industrial system. And so part of that is inherent in the design of the system. The motors we're using are not significantly high torque. They have some compliance. We have hard limits built into the servos that will make sure that if they do exceed the current limitations and operating limitations they have for any extended period of time in terms of like seconds, if not less than seconds, everything goes into a safe mode. All the motors are turn off at the actual hardware supply, power supply. So any error that's sensed throughout the entire arm will cause it to shut down, just as a safety precaution. Some of the other elements to that shutdown that I can mention quickly are one of the things we've encountered over the years with especially industrial arms, but also other manipulator systems, is if there's accidental or through some other operating scenario, a condition where the arm loses power, somebody turns off the power, unplugs the power cord by accident, turns off the power to the motors in one variety of ways or another, it goes limp, and that limp state is often pretty destructive to a manipulator. We've had that a few different times where we've broken elements of a system because someone inadvertently powered it off at the end of the day without thinking about it going limp. And so this arm is designed from the actual base electrical system to prevent that. So when I say that we power off all of the joints in a fail scenario where we have an error that's been detected, that power off doesn't mean the arm just collapses. It means that all of the arms lose power. But what we do is behind the scenes, we actively break those arms so that it very slowly and in a very controlled manner falls down to a passive state. So they're not powered, but we're basically back driving the motors as they are powered off to make sure that they behave in a very controllable way, even when there's no power applied. So in that way, we're trying to make sure that there's no scenario where the arm will completely go limp and crash to the floor. But then on top of that, we have, as I said, protections in the firmware that will make sure that the arm doesn't exceed certain speed and acceleration limits as well as position limits. And then also in our software, we have a variety of limitations to make sure that whether it's in position mode or it's in our external command mode using PWM commands, we're making sure that it's going at a reasonable speed with reasonable acceleration limits and things like that. And that if a collision is detected, we're compensating for that. We are planning on some scenarios to also have limitations built into our software. Obviously, anything that's built into our software examples in MATLAB Simulink or in Python can be circumvented. The limitations that are on the firmware are more difficult. So there's a caution there that we're going to try to make it as safe as possible, but obviously it's an open platform. We wanted to be able to give researchers the same flexibility. But some of the limitations we'll put into what will prevent it from doing things like colliding with the table or things like that, because we obviously can do our inverse kinematics in real time to be able to control those scenarios too. So all that in a nutshell, we're going to do our best to make sure that it's safe and it can be operated right next to a student as they're developing their systems in a safe way, and that we'll be able to detect collisions, detect error scenarios, and power off the arm if necessary, and also prevent them from happening if we can. But from a research standpoint and from an open algorithm development standpoint, some of those can be circumvented if needed for different research purposes. And so we're trying to kind of balance those two scenarios as much as possible.
Another question for you, Pete. Are there any external joint torque estimations? For example, are there any joint torque sensors included in the ARM?
That's an excellent question. We don't have the ability to actively measure torque using a torque transducer. What we do have is real-time current sensing on all of the joints. And so what we're hoping to do, we haven't done this yet, and so we're not entirely sure how well we'll be able to derive the torque commands and torque control scenarios for the ARM using the current sense and torque constants and gearbox configuration and things like that. But we're hoping that we'll be able to do some dynamics and torque-based activities using the real-time current sense, but we're still refining those approaches to see how close we can get to being able to give those real-time measurements in a way that represents the interactions the ARM's having. So hopefully we'll be able to do something along those lines, but again, not obviously with real-time torque sensing.
Another question, is it possible to control the virtual ARM with ROS, C++, and Python?
It will be, yes. The way that we're designing our interface for Python and ROS will use basically the way that it will talk to the physical system will be identical to the way that it would talk to the virtual system. It's the same way that we talked between the two different systems in MATLAB Simulink. So in MATLAB Simulink, when we configure our hill initialize block, which is basically the configuration for the hardware abstraction that's taken care of by Quark, we can add essentially a small parameter to that configuration to tell it to look for the hardware at an IP address, which is local to the system. And that's where the virtual ARM is living, is on that socket connection. We do the same thing with Python. So in Python, you could basically set up your hill interface to talk to the physical system. And with just a small configuration change to the options that you can include with that command to open a connection to the ARM, you can talk to the virtual ARM exactly the same way. So it will be the same scenario in both. In both cases, you'll need to have obviously that connection to the system and have a way to talk to it reliably. But we have done experiments with this where we've been able to do it not just from Python locally to the physical system, but also Python to the virtual system, and also from Python on a Raspberry Pi to the virtual system and the physical system. So we've done some experimentation. We're not at the point yet where we want to publicly release it because we're still building up documentation and things like that and refining our examples, but it is possible, and we'll be hopefully releasing that very soon. As an example of that, just as a side note, our McMaster University collaboration that we've been working on for the last year, for their first year quote unquote pivot initiative, they've been using the virtual QArm in Python on a Raspberry Pi for their entire semester this year. And so we have a very robust system we developed there to enable that configuration. It's slightly different from the one we're going to offer when we release it for this particular iteration, just because obviously we're trying to get that same experience I described, but it is something that's been very successful in that case as well.
Are there any special toolboxes required for the QArm, the virtual QArm?
For the virtual QArm, no. The virtual QArm, we developed the system so that it works with completely vanilla MATLAB Simulink. You don't need any toolboxes at all. If you're doing it in MATLAB Simulink, then the only thing that you would need is our Quark Home, which is a completely free version of Quark that just makes sure that you're able to open our Simulink examples that include our Quark blocks. But other than that, there's no additional MATLAB toolboxes that are needed. And we're designing Python to be the same way, where we may include some examples that call on some external toolboxes and things like that to be able to do some of our operations, but we're trying as much as possible to have the core operation of the ARM possible in just vanilla Python, again, using the same APIs that we'll have available that we used for the MATLAB Simulink approach.
Thank you. Question for you, Pasha. Is the virtual QArm bundled with the hardware, or is there two separate products?
We are very flexible on that, and you can understand where that flexibility comes from. The hybrid teaching approach that Pete was talking about is the exact reason that you have the ability to bundle these together, but you also have the ability to go complete separate ways. So that flexibility exists, and we'll be happy to talk about it.
And also there's another comment related to the curriculum, whether it's free. And yes, our curriculum is provided free of charge with the products.
That's right.
Is there any plan to make a 6 or 7 degree of freedom arm? And is there any reason that we're offering a 4 degree of freedom arm at the moment?
That's a good question. So the reason we targeted the 4 degree of freedom arm was that for this initial release, we wanted to have something that offered all of the different general academic elements that I talked about, basically the ability to have a highly functional gripper, the ability to have that gripper and end effector be customizable using the end effector interface, and our ability to actually allow people to add sensors, add actuation, customize the gripper, along with the camera system and along with all the performance that we wanted to be able to achieve. So basically, at a price point, we wanted to be able to achieve all of those goals. And so this first release at the 4 degrees of freedom, the actuators, to be perfectly transparent, are one of the most expensive parts of this entire platform. And so limiting the degrees of freedom allowed us to be able to hit all of those goals at a very accessible price point. I don't think there would be anything preventing us, now that we've built this first system, to as a follow-up release 4 degrees of freedom down the path if that is a need for most of the scenarios, especially for teaching, but also for a lot of especially modern research initiatives, things like what I said, machine learning and Industry 4.0 and those sorts of activities. More than 4 degrees of freedom aren't necessarily required. They're nice to have because obviously they give you more flexibility in terms of how you track objects or do very particular approaches to pick and place or things like that. But that does, to a certain extent, once you get into 5, 6, 7 degrees of freedom, start to kind of pigeonhole it into certain types of activities where you're really going to use all of those degrees of freedom. And so because we wanted to kind of have a more general approach that was also cost effective, that was why we thought 4 degrees of freedom would be enough, as well as to be able to do almost all the activities you'd want to do. And then obviously we could customize it more to be a little bit more flexible, but then also at that point, there's other options that we'd have to look at in terms of that kind of very specific high performance manipulator system. What I think, to be honest, we probably would do next would be to do a manipulator system that's smaller, that has a much lighter form factor and much lower power requirements. That could be something we could mount on one of our ground vehicles or aero vehicles. That's something that we've been asked about a lot. And I think, to be honest, the approach we've taken, because it's pretty modular and scalable, that might be our next step, would be to do something actually the opposite direction, to be smaller and more power and energy and weight efficient, to be able to have it mobile. But that's just a little side note that no promises, no guarantees. You're not going to see it a month from now, but that's what I think we might go in next.
Could you comment, Pete, a little bit further on the interface at the end effector? Could someone, for example, add a force or torque sensor for the gripper? And if so, what sort of a speed bandwidth limitations are there?
That's another great question. So what we basically did at the end effector with the interfacing board is we exposed a number of different channels for communication primarily, but also for measurement, so that the same way that you would use something like a Raspberry Pi or an Arduino, you can interface a variety of additional sensors or actuation elements or things like that to be able to customize what's going on at the end of the arm. The scenarios that we envision would be things exactly like you said, like adding additional pressure sensors or force sensors, being able to add additional range finding or depth-based systems, maybe something like a LiDAR, to be able to do more mapping and localization, a number of different activities. And to suit that, what we've done is basically provided regulated power at 3, 5, and 12 volts, as well as pinouts to be able to do off-the-shelf I2C, SBI, UART communications to our API and to Quark. So you can basically talk to those pins in a very intuitive way. They are just basically DIO pins, so they're somewhat flexible and customizable. They'll have a default, but you'll be able to customize those if you see fit as well. And also generate PWM commands and measure PWM or encoder counts. So a lot of flexibility there. with the goal of being able to add electrical components at the end effector. The specific example of the torque sensor or torque measurement to be able to add to the gripper, that's definitely something that you could do. It would obviously depend on the interfacing requirements. I believe the bandwidth we're going to be aiming for, we're literally developing those elements right now. So I can't give you a very specific idea of what the targets are or what the abilities are for being able to do those communication tasks. We're going to try to get them as flexible as possible so they'll be able to be used with a wide variety in terms of baud rates, but I can't tell you right this second. What I can tell you in terms of those speeds is that our external control loops that we're running in MATLAB Simulink and Quark in real time interfacing to the joint system, those are running at 500 hertz. That was a limitation again that was part of our certification requirements, was to limit those at a level where we weren't getting emissions and things like that at higher rates. But those are running at 500 hertz. I think probably the communications we're hoping to run in parallel to a certain extent, which could open up higher speed communication, but it's never going to be high enough to be able to do like video streaming. But we'll try to achieve a level that will allow us to interface most sensors or actuation systems that you would want to be able to use on that kind of scenario.
Another question, is the ARM suitable for investigating more advanced topics such as deep learning and optimization?
I don't see why not. Again, like we're trying to make it as open and flexible as possible. So as long as those algorithms, whether they be in Python or MATLAB or whatever the platform is that you're using, we've always tried to make it as easy as possible to expand out those types of topics and not have to worry about the hardware interfacing aspect of it. Basically, to be able to focus on the activities that you want to do and ignore what you're not concerned with. And so being able to expand it out to other toolkits or other platforms about MATLAB Simulink should be no problem. And the same for Python. It's essentially, we'll build out enough examples that the actual operation of the ARM will be pretty straightforward, and whatever algorithms you want to implement with whatever additional toolboxes, you have that flexibility to add those to whatever examples you're using. As a side note on that particular point, the camera, we're not actually streaming the camera through the same USB connection as the rest of the communications. It's a separate, basically what we've done is we've routed the USB connection to the camera internal to the ARM, but just exposed it at the bottom of the ARM. So there's nothing, basically when you plug in a USB connection, USB 3, to the camera connector on the base, you're talking directly to the RealSense camera. There's nothing in between. So you can use that camera for whatever application you like, and either in parallel or at the same time operate the ARM the same way. There's no limitations there.
Awesome. Are there any plans to have LabVIEW support?
That's a good question. um, I honestly don't know. To be perfectly honest, we could probably allow some level of interfacing in LabVIEW if that was something that we are getting asked for. At the moment, we primarily targeted MATLAB Simulink as our main focus for release, because that's where we get the performance and the guarantees in terms of safety and reliability we look for with a system like this through Quark. In addition to that, we're going to definitely, as I said, be targeting Python and ROS, because that's another very strong market where a lot of research and teaching is done. But if LabVIEW starts to come up as a platform that the people want to use this type of system in conjunction with, it is something that we could do. We have the ability to take our library calls and our APIs and figure out a way to talk to LabVIEW that way. One thing I might recommend in terms of the easiest approach to using LabVIEW would be with something like a MyRio or a CRIO in conjunction with our embedded interface, which we'll also support in the coming months. You could very easily create a LabVIEW controller or LabVIEW external system, deploy it to a Rio platform, and then talk to the ARM through our embedded interface. That'd be much more straightforward in terms of both performance and also that should be something that's possible very soon as we release the embedded interface for the ARM as well.
All right, I have two more questions. First, is the ARM suitable to teach dynamics control, such as the computed torque control for a joint?
So that's sort of along the same lines as the previous question in terms of measuring torque. We hope so. Our goal is to develop some examples of dynamics and show how dynamics comes into play with these types of systems. It's not generally something that we find is taught in the undergraduate courses. It sometimes is, sometimes it isn't. It sort of tends to be optional in terms of whether or not those types of chapters from your traditional textbooks are covered. We would definitely like to, but as I said, we're still at the point where we're trying to determine how accurately we'll be able to represent the dynamics of the system with the real-time measurement that we have from the real-time current that we're measuring at the different joints. So we're hoping that we will be able to do that. We're still at the point where we're not 100% sure. We have to do some more work to see how accurately we can represent those torques. But we could also, as a side note, if that isn't something that we can do on the physical system because of the limitations of our current, we could definitely do something like that in our virtual representation quite easily, given the dynamic models that we're using there to represent the system. And so that is also an option as well.
Awesome. And final question, are there any other virtual products that we offer, such as Virtual Cube Servo 2?
An excellent question. I'm also, by the way, the project manager for our virtual experimentation platform, so that's right up my alley. Yeah, we offer a lot of our experiments now as virtual representations of the system. From the robotics perspective, we have both the QArm and our ground vehicle, the QBot 2E, that are available as virtual plants. We also offer our controls experiments, things like the Aero, the Cube Servo 2, the rotary servo base, with the optional attachment of the ball and beam. Next week, we're hoping to release also the flexible link for the rotary servo, and then finally the coupled tanks. So there's a whole variety of platforms we offer with exactly that high fidelity, dynamically accurate representation of the system. And then on top of that, we also have a complement of activities that we call QLabs controls that offers experiences for students that are built into the platform itself without any need for MATLAB Simulink or any external development. It's all built into the platform itself where they can experiment and learn about control systems in a very turnkey and very easy way. And that's that's applied to the Cube Servo 2 with both the disk and the pendulum and the Aero. And that particular package, the simplistic parameter-based QLabs controls approach, that's available for not just Windows, but also macOS, iOS, and Android. So there's a whole lot of flexibility there. But then for the MATLAB Simulink approach, the customization and being able to port the experiences like I showed you from the physical system to the virtual system, that is available for Windows, and that covers all the plants I mentioned. So we've been doing a lot of work on that respect, and what we're sort of going to be, we're going to be expanding that out in the future as well. So stay tuned for that.
Awesome. Well, that wraps up our presentation. Thanks again, Pete and Pasha, for this amazing presentation, and a big thank you to all our attendees. As Pete mentioned, if you do have any questions, please contact us via email or visit our website at www.quanser.com. Have a wonderful day and stay safe, everyone.